Hi, today we're going to be looking at a geometrical proof looking at concyclic quadrilaterals. A concyclic quadrilateral is a quadrilateral where each of the four vertices sit on the circumference of a circle. Before we get to this proof, it is a good proof, there's a theorem we need to prove first. Here it is. Let's say we have a circle and we have some segment here. There's an angle in the center of the circle, okay? And here on the circumference we're subtending the same segment. The theorem is that this angle is double this angle. So let's go ahead and prove it. So I've got the diagram here. What I'm going to do is extend and then continue a little bit this line. So here's my point D at the center. Now this angle ABC has been split into two segments and I don't really know what they are, so I'm just going to call one of them X and the other one Y. They don't have to be even. And note that also the angle ADC has been split into two segments, okay? And they are not necessarily the same. So I'm just going to call them alpha and beta. Okay, so note, here's the first trick. Because we're on a circle, these three lines are radii, okay? And I'm going to use just a shorter notation instead of giving the full angle name. For example, this angle here, I'm not going to call it angle BAD, I'm just going to call it angle A. Okay, this will be equal to that other angle, and the reason for that is we have isosceles triangle over here, because these two are the same. Cool, so we're going to do the same thing down here. So the angle at C So I've just realized that I should probably be labeling these ones properly. So I'm going to call this angle DBC. And this one will be angle DBA. Okay, so now note that this angle alpha is the external angle to this triangle, and so okay, that's using the external rule that the external angle is equal to the sum of the opposite two internals, and then we'll go ahead and do the same thing. Okay, and now finally, that angle that we're after, we have angle ADC is the sum of alpha and beta. Which comes out to 2x plus y, which is 2 times the angle ABC. Awesome. So we have that proved. And now we can go ahead and look at cyclic quadrilaterals. Okay, so here is a cyclic quadrilateral. You can draw one of these, just take a circle, pick any 4 points, and there it is. Here's the test for cyclic quadrilaterals. We have that these points are cyclic if and only if the opposite angles are supplementary. So add these together, we get 180, or add these together, we get 180. Okay, let's go ahead and prove this. So note that this proof is an if and only if. It works both ways. So we'll first have to prove one way, That is, we start with the cyclic quadrilateral and then show that the opposite angles have to be supplementary. So we'll go ahead and do a quick construction. Okay, and I'll just put our center here somewhere of our circle. So we have a put the center here at E. Okay, so going to draw a line through, as we have here, and note that there are two angles, alpha and beta. By the previous theorem, this angle at A subtends the same sector as the angle at beta. Okay, so we have that. So if I double that angle at A, I get the angle here at beta, and then I'll apply the same theorem here. If I double the angle at C, I get alpha. This is by previous theorem. Okay. Now we also have the fact that alpha and beta sit on a full revolution. So because they sit on a full revolution, they add to 360 degrees, and then okay, so just by a bit of rearranging, we get that the angles A and C are supplementary. This is sufficient to show that B and D are supplementary because we're on a quadrilateral, so everything has to add to 360 degrees. So we have okay. Because it's a quadrilateral, everything adds to 360 degrees, and B plus C make 180, so we have A plus C. Okay. And then from there, we have the fact that B and D are supplementary as well. So we've proved it one way. Okay, now let's go the other way. Let's say that we have a quadrilateral with supplementary opposite angles. We then have to show that all of its vertices lie on a circle. We don't know this, so let's do a proof by contradiction. So we have a circle. We know that if I pick any 3 points, they have to lie on a circle. The question is, for a fourth point, will that lie on a circle? So there's a standard construction for 3 points, which works. So let's assume we have 3 points on the circle, but that fourth point might be off the circle somewhere. It doesn't have to be on the circle, but they form a quadrilateral. And then note that on this line segment, we have to intercept the circle somewhere, right? Because here we're on the circle, here we're outside the circle. So I'm just going to call this C star. And then the goal will kind of be to prove that C and C star have to be the same thing. Okay. Well, if I construct this, then I see that I have 4 points which are on the circle, which are, okay. So, let's see. I'm going to take this angle down here and just call it X. Okay, could be anything. Now, so we had to do the other proof first that's involved in this proof. We have a a cyclic quadrilateral here. That means that this angle must be supplementary here, and we have 180 minus x. Okay, but then we also have that this is a opposite angle supplementary quadrilateral, and so this has to be 180 minus x as well by definition in our proof. But here is the, so I'm just going to call this angle y. We don't know what it is. Here's the contradiction. This angle here is external to this triangle that I've made out here, so it has to be equal to the sum of the internal angles. In other words, we have 180 minus x equals the same thing, 180 minus x plus y. But this is a contradiction, right? We could say that y is 0, and that corresponds with bringing this, you know, away from being a triangle, just down to a line. Or we could simply say this yields a contradiction. This is a contradiction. And therefore, our assumption that C was off the circle must be incorrect. And and then that quadrilateral must be cyclic. Cool, okay, so I hope you had fun. We did a good proof. Have fun, and I'll see you around.